Hi guys, welcome back to Mr. Allen's class here. So today we're learning about logarithms. Now, what you need to know about logarithms, well, it's actually quite a bit, is that the key thing is that they are the inverse of an exponential function. We know a bunch of inverses already. We know the inverse of a square is a square root. The inverse of a reciprocal is a reciprocal. What an inverse does, or the inverse is a plus, is a minus. It just undoes that operation. It makes it so we can solve for whatever's inside that operation. So let's say if we're solving for an x, that's an x squared. Take the square root. Now I can solve for x. Now, an inverse of an exponential, say this is my original exponential here, right? What you're going to do is you're going to switch your x and y's. But to do that, to switch your x and y's, it's not as just easy as just putting your x and the y into different spots. Is that what you would do is you switch your x and y's and then solve for y. So here we've done it already. We switched the x and y's, but now we have to solve for y. And to switch between the two, we just use what we call a logarithmic function. It's a different function that allows us to solve for this y. Because it started off as y is equal to c to the power of x. We switched the x and y's. You can see that's what happened here. So remember, y is equal to x. When we do that inverse, we've reflected it over the line, y is equal to x. Sometimes you could say f of y is equal to x. That's another way of just saying the same thing. We switch the x and y's. So it becomes what we call a logarithmic function. And it is a function. It does pass the vertical line test. It will have a vertical asymptote on it now because of how inverses work. If an exponential function has a horizontal asymptote, then the inverse will have a vertical asymptote. All the domain and ranges will switch. X and y intercepts will switch. Every single x and y will switch no matter where they are.
Cole Smith to room 2505, please.
All right. So now what we have here, we have what we call the logarithmic function that allows us to solve for this y. After we switch the x and y's, now we have to solve for y and get y by itself. That's how we did our inverses before. We switched them and then we tried to rearrange the equation to get the y by itself. So this line, when you see this line, y is equal to log base c of x, that's literally how you're going to write. Y is the logarithm to the base c of x. Now, log base c here, this piece, is very similar to like sine and tan. It's like a function call. You have this function, and then you're going to put something inside that function, very similar to what you did here. So like the sine of 0 or the tan of 130 degrees or something, right? So you put something inside those functions, and it's going to spit something out. So you're going to put x into this function, and it's going to spit out y. Now, it's not a thing that you can just divide over. It's a function. It's not like when we solve for sine, you can't just divide the sine piece over. You'd have to take the inverse of the sine, which is called the inverse of sine, to get this piece out of here. So this is not a number, it's a function. So I'm not allowed to just divide that over. All right? Now the c is the base. You can see this is my base here, right? This is also the same base here, the same number. Right? The most common base that we deal with in this course is base 10. That's not the most common base in mathematics. The most common base in mathematics is e. It's the natural number. It's Euler's number. But you'll deal with that more in calculus. And if you ever take Math 3-2, you also deal with it in Math 3-2 as well. So, the base 10. Okay, so that's usually what it is. And usually if you don't see the base 10, that's not there. So if someone writes log of x, it is assumed to be log base 10 of x. So if you see an absence of a base here, that's assumed to be 10. So if you look at your calculator and you look at the log button, which says log, that's a log base 10 on your calculator. I can show you what it looks like here. Let's move my face sliders. So you see this log button right here. Okay. So when you see this log button, that assumes to be base 10. The one below is called a natural logarithm. And you don't deal with that one until you get to calculus or so. All right. All right. So these ones here, you can actually just do the opposite. Like 2 to the power of 3 is equal to 8. Right? But let's just see how this could work if I want to change between the two. And the reason you want to try to change between the two is you want to solve for whatever's in the exponent, like down here in E, F, and G, or even B, there's this unknown exponent. So to change this, it's pretty easy to do. So you identify what the base is. Here's my base. The base is 2. So I know that this is going to be a log base 2 because the original base is 2 on this as well. Then you're going to just switch these positions. This is equal to 8. Now it's going to be equal to 3, right? And then the 8 was inside, or so the 3 was inside the function, but now the 8 is going to be inside the function. So log base 2 of 8. Right? Now we can actually verify that by calculating this. So log base 2 of 8. To get the log base 2, now there's two ways to do it. Like if you have one of these newer calculators that have been updated a little bit, you can actually find the log base in, if I can remember where it is, I believe it's under math here. Let's go down a little bit more. There it is right there. All right. So under math, you hit math, you go down to A here, it says log base. You hit that. Oop, you probably want to be out of the graph to do that. So math, so log base. And then it could allow you to put a 2 there, and put an 8 here, and it should spit out a 3. There it is. So what this is asking your calculator says, if my base is 2, what does my exponent have to be 8? So 2 to the power of 3 gives me this 8. That's what it's asking your calculator. You're asking your calculator to figure out, what do I have to raise this base to? What exponent does it have to be what this number is that I put into this thing? It spits out 3. So this works. So it works out. Now, if you have an older style calculator and you don't have the base number, like most calculators do, like this kind of calculator, doesn't have a base changer like this, right? So you can use what we call a log identity to change them. We can use this rule. So these calculators can do base 10 or even natural logarithms that works the same way. So you can use the ln button to do the same thing. But we can use log base 10. So what you're going to do is you're going to take these two logs, one log 8 and then one log 2, and just divide the 2, and you should get a 3 as well. Now you'll notice that this is down here on the bottom, this is on the bottom as well. So those two things are on the bottom, this is on the top, and this is on the top as well. Okay? So those two things are the same calculation, same operations. Okay, so we could do the same thing with this here. So we could switch the spots of the 4 and the 81. So I could say 81 on this side instead. And then on this side over here, we have log 3 of 4. Oh, my bad. Sorry, I did that in the wrong spot. I was trying to figure out why that didn't make sense in my mind. So we are switching the two spots. So this 4 comes out of the operation, and we put the 81 into the operation. So that's what it ends up being here. Sorry, there should be a 4 there. You can punch it in a calculator and make sure that actually works. So I'd practice that. So let's go check that out. Math, go change my base here. Nope, let's go up 1, sorry. And what do we have here? So we had a log base 3. So what do I have to raise 3 to the power of to get 81? Let's see, we have 4. Okay, so far these all kind of work. And you could just do that by changing the base technically. Just change the base to 3 to the power of 4, and then it kind of worked out. Works with negative exponents as well. So you notice that here, my base is 2. Here my base was 3. Okay, so my base is 2. So let's write it on this side this time. So log 2, and then we're going to switch these two things. So I'm going to put the 164 on this side, and the negative 6, which is part of the operation here, the exponent of the operation, is going to drop out, and we're going to get that. So these two guys will switch your spots. You can do the same thing. This is the more general form. Like, what do we do? You notice my base is A. So this is my base. So this is going to be the log base A. And then these two guys here are going to switch their spots. So the C is going to go into the operation, and the B is going to pop out. So this is supposed to be A right there. Okay, let's move this out of the way. Now, why is this useful? Well, it's useful It's not in these cases, it's not very useful in these upper cases, but it's more useful when you're trying to solve for an exponent. Okay? So I want to know what y value do I have to put here when I do this math to equal this number that could be over here. Like you see on G here, they give you everything, but you don't know what T is. One thing you should know before you start this is that in this changing between the two, so if I just scroll up here for a second, you notice that there is no a value here. A is equal to 1. So this a value doesn't exist. So I can't really change between these two forms if there's something in front of my exponent or my exponential form. So you notice there's a 2 here when we do this one. There's a 2 right here. So to fix that, just divide the 2 over to the other side. So you get a over 2 on that side. Now, because there's nothing in front of my exponential form, I can use this and I can change into my log form. So my base is 10. So that could be log base 10. Or you don't have to write the divide by 10 or the 10 here in the base, because if it's not written, you assume it to be 10. And then you switch the two sides. So the y, which is part of this operation up here, because it's 10 to the power y, so that's the operation, it's going to drop out. It's going to become equal to y. And then over here, because it was equal to this number before, that gets put into the operation. So they switch their spots. Yeah. So the same thing works if I just have variables, but I can't have an a value here. So I got to divide that over to the other side. In this case, at the b. And then I can switch the spots. So this is log base c, and then it's a over b. And then this is equal to d now. Okay. There's a little funny little tick there. Okay, so let's see how this actually works. So like we have this, maybe I'm trying to solve for what t actually ends up being. Like what t value do I have to put here? So when I do all this math, I get 600,000, all right? So we're gonna do the same thing that we did over here with the 2. We divide the 2 over. So we're gonna divide the 500 over first. So we take 600,000 and divide it by 500. Yep, okay. So when I do that, well, let me just wait till my thing actually works. Okay, so when we do that, we get 1,200 here. So we divide over the 500 to start off with, because we want the exponential by itself. Then, because what we're trying to solve for is in the exponent, we couldn't technically just graph this and solve for t, like we've done in the previous lessons. Right now, we're trying to solve this algebraically. So we're going to use what we call logarithms. So we're going to recognize the base is 2. So this is log base 2. And then we're going to switch these two things. So this exponent is going to kind of drop down over here. So you get t over 80. And then I'm going to put 1,200 into this spot. Okay. And then, I'm running out of space here, we're going to solve for t. Right now this t is divided by 80. So we're going to times both sides by 80. And we're going to put the 80 in the front. And now I can solve that. So I can go over here and I can say 80 times math, I'm going to go down to a here, log base 2, 1,200. And then we hit enter. 818-ish state, or whatever this happens to be. I don't know what this ends up being, but it's approximately 818. If you want to, you can go back and verify. You put 818 in this little box up here. Should work out. Okay. Now, I can change from exponential into log, but can I change log back into exponential? Now, sometimes that's useful too. Like here, down here, I want to solve for what basis is, right? Or solve for what n is. In this case, I wouldn't have to do that. Maybe I want to solve for what x happens to be if I know what y is. So you can always just switch it back. Right? So the first thing you want to recognize is what is the base. Now this one doesn't have a base written here, so my base is equal to 10. So this would be 10 to the power of something. And then these two guys are going to switch their spots. This is equal to -2, but now that's my new exponent. And this 0.01 was inside the function, so now it's going to pop out. Yeah, mathematically that looks good in my mind, so that's good. So here's my base is 2. So I know this is going to be 2 to the power of something, and then these two pieces are going to switch their spots. So this is to the power of 3 to the y, or 3 2 to the power of 3y, sorry. And then it's going to be x plus 1. Okay, the same rule applies from before. Now, if there's an a value in the front, we got to get rid of that a value first. We're going to divide both sides by 2 to start off with. All right, so let's get this over here. So this turns into a 3. And now, because there's nothing in front of the log, I can change it back into exponential. So this is going to be b to the power of 3 is equal to 8. Now, if I wanted to solve for b, I just take the cube root of both sides. B is 2. So let me just write that in there. We get the cube root of both sides. We get b is equal to 2. All right. So we do the same thing on here. There's no a value in front of this log, so that means I could just switch between the two. I recognize the base is 1.05, and then I switch these two things. So now this is to the power of n is equal to 2. Now this was not as useful because now what I'm looking for is actually an exponent now, but maybe that's just how we're going to write it. Maybe I can graph this side over here and look at more different, or looking for different values other than 2. Okay. Now, here are a couple special cases. I'm not going to go through too many of the proofs. If you want me to prove some of these later on, I can. Actually, maybe I can show you a few of these, like why is the log base of 1 always equal to 0? All right, so the log of 1, any 1, doesn't really matter what the base is, will always be 0 because it's just the same rule as y is c to the power of 0, always equal to 1, because that's what you're thinking. What do I have to raise c to the power of to get 1? Well, I always have to raise it to the power of 0. So if I could change this to exponential form, this is what it's saying. C to the power of 0 is 1. My base is c. I switch these two, and that's that statement. So if I see this log of 1, that'll always be 0. Now, it's a very useful thing, too. If there's a 0, I can always reintroduce that. I can put that in there if I just want to add a random log for some reason. Now, log c to the c, log base c of c, follows kind of the same logic. 1. If I change this to exponential form, my base is c. Okay, so that's the same base there. I'm going to switch these two. Okay, so that's to the power of 1. And c to the power of 1 is c, which makes sense. So this is going to be true. So that could be any base. It could be 10 to the power, or base 10 of 10, base c of c. Now this operation is super important. This shows up quite a bit. You can introduce that as much as you want. So you could say like the number 10 is technically 10 log base 2 of 2. Why did I pick 2? That's just a random one. I could have said 5 of 5, 10 of 10, c of c. I can just reintroduce a log whenever I want. There's a reason we'd want to do this much later on, way down there in our lessons. Okay. Other ones here kind of follow the same logic. So if you look at log base c of c here, of c to the x, I'm just going to put brackets around that because that's what it's supposed to look like. If I change it to log form, is it true? So c, and you're going to switch these two spots. So this x is now going to become the exponent, and this is going to drop down the other. That's a true statement, just like all these other ones. These are all true statements. So this will always happen if I see this. And there's other reasons. We could shortcut this, not other reasons, but there was a rule later on, a log law, that we can just drop some exponents down and it'll just work out. Now this one here, but the same way as the previous one. It's a little bit trickier to think of, where this, you can become a y. So you could say, let me just, maybe I'll erase something here. I'll just go through it really quickly here. So I can change my exponent to be a y instead of that, really say y is equal to log base c of x. That's what I'm going to say. Okay. So what I'm going to do now is I'm going to change this into log form. All right. So my base is c. So this is log base c. I'm going to switch these two spots. That's equal to y. But I just said over here y was equal to log base c of x. And this also says y is equal to log base c of x. That's a true statement as well. They're both exactly the same thing. So this statement also works. No matter what x's and c's I use in there, that statement will always work. Now it's not as useful, but sometimes it pops up. Sometimes you will see that where that little exponent can pop out, or this inside the log can also pop out. So what we're going to do with these is we're going to try to, well, like I showed you, you could just punch in your calculator and get an answer. So you can go down here, use log base 4 of 64, and actually get an answer out. But we're going to evaluate these without using a calculator as much as possible. So to do that, maybe I'll just make this equal to y, and then change it around. Okay, so let's change it into exponential form. So my base is 4, y to 64. You're like, what? That didn't help me too much because now the exponent is y. Here before it was equal to y, I can just punch in my calculator. But we've done this before. We could change our base. 64 is 4 to the power of 3. And then because the bases are the same, y is equal to 3. All right, I punch in my calculator and get the same solution. You could think logically, that's what it's asking for. Like, what do you have to raise 4 to the power of to get 64? It's the same idea here. My base, because I don't see it, is 10. So it's asking me, what do I have to raise 10 to get 10,000? Okay, and then I can change that to base 10. So y is 4. Okay. Same idea. What do I have to raise 3 to get to 81? If I want to change the base of 81 to 3 to the power of 4, y is also equal to 4. Yeah. If we make these things equal to y. Let's make these equal to y. Okay. So we're going to do the same thing. We're going to make this equal to y. And then saying, what do I have to raise 3 to get 1 over 81? If I change the base, I can change this to be a negative exponent and then change the 81 like we did over here. Way in that top corner, way over there, way over there. All right, change the 81 to 4. So this could be 3 to the power of negative 4. So that means y is equal to negative 4. Same kind of rule applies with these. Sometimes it's just easier if you could take the square root of it first before you start doing it. Like, what's the square root of 16? Well, that's 4. And we have a rule that's up there that said log base c of c is always equal to 1. All right, so what do I have to raise 4 to the power of to get 4? So 4 to the power of 1. All right? What do I have to raise 2 to the power of to get the root of 32? Now this one's a little bit trickier because the square root of 32 is not a nice number. But we can change that to base 2. And remember, the root is also a rational exponent. So 2 to the power of 5. Oh, 2 to the power of 5. That's a y there. Square rooted has to equal to the y. So y, if I drop my base, is 5/2. So you're just going to multiply your two exponents together. Yeah, and you can have fractions come out. That's fine. Yeah. Let me just give it a little bit of time here to think. I might have to refresh my computer here very soon. Getting to the bottom of this example page here. Okay. Yeah, maybe I'll. Yeah, well, after this page here, we'll stop for this video. So, what do we have here? We want to evaluate these now. So we can evaluate these in your calculator, like these ones here. Well, I'll come back to that one later. Okay, so to evaluate these, we could also do the same thing, make it equal to y. And we could change it into exponential form, but that's not going to help us. Maybe it'll help us a little bit. We could say, okay, 7 to the y is equal to 1. What does y have to be to make this equal to 1? Well, the only number I can think of is 0. Remember, that's one of our rules at the very top there. If I take the log of 1, it's always going to be equal to 0. So here's the log of 1 again. So what I know is that this is going to be equal to 0. Here's the log of 6 of 6. We have that rule right here, like right in the middle of our page at the top. Log 4 of 4, log c of c, that's going to be 1. Now this one here, if I make this equal to y, remember this is one of our rules. So what I know, if I remember the rule, it should just equal 3. Well, let's just double check. So I'm going to change this to exponential form. So it's going to be 5 to the power of y. What do I have to raise 5 to get 5 to the power of 3? Chop my base. Y is equal to 3. Yeah. This one here, I kind of think it's going to be 32 based on one of the rules at the very top of the page here. But let's just double check. So if I make this equal to y, make this whole thing equal to y, rather than saying equal to 32, this is equal to y. Let's change it into log form. So it's going to be a log base 2 of y. So I'm going to switch these two sides here, and I'm going to drop this exponent down. Log base 2 of 32. Now, this has the same reasoning as y 2 to the y is equal to 2 to the 2, and y, these have to be the same. Everything here is log base 2. This is log base 2. So what's inside these two functions have to be the same to be equal to each other. So y is 32. That one's called dropping the log rather than dropping the base. So if we drop the base over here, in this case, dropping the log. Okay. Follow the same rule of logic as the one we just did. These two bases are the same. So this should equal 10,000. The same rule, if you just want to do for E, you could, but maybe the same thing. Yeah. So our next video, we're actually going to cover changing bases. And we're going to start our identities and different rules. So I'll see you in the next video. Ciao.